And just like that, we made it to the last lecture of this course. On this lecture, we are going to be covering buffers. And what we want to learn is how a buffer resists changes on pH. So that's what a buffer is. A buffer is a solution that resists changes to pH. And it's super important because a pH of 7.35 all the way to 7.45 is the normal pH of your blood. Goes below 735, goes above 745, that means trouble, big time. That means you may die if you don't correct that. So being able to maintain a pH at a specific range is super important. Your body have a lot of buffer systems that prevent the blood from getting out of that range. From a chemist point of view, if I'm trying to run a reaction that needs to be running at a specific pH, I better prepare a buffer that I use to run that reaction so the reaction stays within that pH. Because in organic chemistry, a higher or lower pH can affect the molecule I'm trying to build. Engineering applies this concept a lot also. But the one I relate more to is my blood. So it's super important that I maintain my blood around that pH. I do not have to worry about it because my body have the mechanism to do that because my body contains buffer systems. So at the end of this lecture is when we're going to see how that works. So before we get there, we have to understand a buffer system better. For example, what makes a buffer? How do we know we have a buffer? And the answer is simple. The first thing that you need to have a buffer, you need a weak substance. That's why it's so important that we need the strong ones because everything else is weak. You need a weak acid combined with its conjugate base. So that's what we covered at the beginning of the chapter because you need to understand what a conjugate base is, or you need a weak base with its conjugate acid. So on the system, on the container, on the solution, you have to have both of them present at the same time. The acid and its conjugate base, the base and its conjugate acids. That's why we cannot have a strong acid or a strong base because a strong acid, a strong base transform 100%. So you're not going to have, if you begin with a strong acid, it's going to become its conjugate base with nothing left of the acid. So that's why it has to be a weak system. So the problem that we have, determine whether each mixture is a buffer. So it has to be weak and it has to be combined with its conjugate. So the first one, HCl, that's strong, so do not check anything else. That's a strong acid. If you were on my science for my chemistry for science majors, I will not tell you that because we can make a buffer using those two substances, but for our purpose, if you don't have a weak system, it's not a buffer. The next one, the same thing, that's a strong base. So you see how important it is to know our strong bases and our strong acids? Immediately you can eliminate that. That cannot be a buffer system. The next one, we have a weak acid. And if this is a weak acid, it will lose a proton and its conjugate base will be that, right? I do not see that there. Oh, or are you sure? Actually, it's there. Because remember, all this is happening on aqueous solutions. So NaF, as you learned in a previous chapter, NaF, when you put it on water, it's going to separate, it's going to be soluble, giving you that. So we will never find this by itself. Ions do not exist by itself. you will need to have the salt of your conjugate base. So always look for the salt of the conjugate base. Salt of conjugate base. That's what you can find on your chemistry supermarket. You will never find an ion by themselves. So this will be a buffer. So this is a buffer system. And the next one, let me clear the screen a little bit. It's getting too crowded. The next one, this begins with an A, so that's an acid. Do we have its conjugate base, which is basically everything but the acid? And we do, because this is a salt in water, it will separate. So this is also a buffer system, where you have the acid and its conjugate base. So two of those solutions are buffer systems, because you have the acid and its conjugate base present, or the base and its conjugate acid present. So go ahead and work on those four. Remember, eliminate the strong ones first, they cannot be strong, and then make sure you have the acid and its conjugate base, or the base and its conjugate acid. So on this learning check, we're gonna see what do I need to add to this to make it into a buffer solution, where we already know that it had to be the acid and its conjugate base, or the base and its conjugate acid. So we have to see what we have. This is a salt because it has sodium, a metal, and non-metals. So when we put that in water, we know that the metal is going to separate. Na plus, so this has to be Na negative. Okay, so all I need to do is add the corresponding acid. So I can go to this chemistry supermarket and find that acid, which is going to be an aqueous solution, and that will give me a buffer. This one is also a weak acid, so I'm going to need the conjugate base, which is going to be losing one hydrogen, right? Which means I will need something like sodium phosphate, because I cannot find the ions on my imaginary chemistry supermarket. I always find the salt. They always have to be together. So I will put that, and that will give me a buffer. And this one is also an acid, so I'm gonna need to find the conjugate base, but it will have to be with a metal to make it a salt, and that will be what I get. So we're doing nothing more than making sure that we understand that a buffer has to contain the acid and its conjugate base, or the base and its conjugate acid. So go ahead and do that. Make sure you recognize what you have and what you need. Do you need the acid, or do you need the base, the conjugate? And once we do that, now we are ready to understand how a buffer works. Write reaction showing how each of the following buffers, so weak acid and its conjugate base, weak acid and its conjugate base. Notice I got rid of the metal right away. So this is the way it works. I'm going to show you how it works, and then we're going to do the reaction. If I have a beaker that contains a solution that contains HF and F negative, this is an aqueous solution. So this is actually reacting with water, producing hydronium and F negative, and this is actually reacting with water, producing hydroxide and HF. You see how we ended up with the equilibrium expression. So we have both of them, so we have both of them present at all times. And now I'm gonna go eat me a very strong lemon, which is very acidic. So I'm adding hydronium. So as soon as this hydronium goes in there, the hydronium concentration of my solution is increasing. So my pH is changing. But a buffer is not supposed to allow that. So what's going to happen so that doesn't happen? So as soon as the hydronium goes in, it's going to go for the hydroxide and it will become neutralized. And the hydronium is gone and my pH goes back to normal. What about if I add a base? So if I add a base, let's say that for example, right? If I add a base, my POH, not my POH, sorry. If I add my base, my hydroxide concentration will increase as soon as it makes it to the water, right? Which means it's gonna make the pH higher, making it more basic, but a buffer is supposed to resist that. So what's gonna happen? As soon as the hydroxide goes in, the hydronium that my buffer is producing is gonna cancel, which means it's not gonna go up, which means it's not gonna go basic, and it's gonna remain the way it was at the beginning. So that's what's happening. Your buffer contains an acid and a base. So if you put base in there, the acid part of the buffer will neutralize it. If you put base in there, acid in there, the basic part of the buffer will neutralize it. So as long as the amount of as long as the amount of the acid and the amount of the conjugate base are more or less equal, this should be a very effective buffer system. So what about writing the reactions? Well, I'm gonna have HF in water producing, it's a weak acid, so it's 2 arrows, producing hydronium and H negative. And now I'm gonna add HCl to it. So when I add HCl to it, the HCl will react with the fluoride, producing HF plus Cl negative. So it doesn't give a chance for the HCl to make more hydronium. What about the base? Since I have fluoride in there also, when I add the acid also, adding the acid now to that part. Actually, that's the part we saw. Actually, yes. Sorry for that. So the F negative will react with the water, right? Producing HF and OH negative. So if I add OH negative, instead of these two combined to increase, it's gonna react with the HF, producing F negative plus water. So at no moment, at no time, the OH concentration increases because immediately it's transformed into water. So that's how we represent that with a chemical equation. And now you should be able to work on those two problems. Don't focus so much more on writing the chemical equation, but on understanding the chemical equation, on why it doesn't go more basic, why it doesn't go more acidic. And once you do that, we have come to the end of the last objective, which means we have come to the end of the last chapter, which means lecture-wise, we have come to our last lecture. I would like to say Thank you for hanging in there. I hope that these lectures have been good for you, that you have been able to get information out of them. It has been a tremendous experience for me. This is the first time that I do this amount of recording for every chapter that I teach. I know I will be able to use this. Actually, I'm going to be teaching this during the summer, so I'm going to be reusing all this. So it's advancing my teaching style a lot. So thank you for allowing me to do that. So I will be posting soon the message for this week, and then we have final next week. So hang in there. If you're here, that means you're doing really well, or at least you're persisting, which is the most important part. So let me know if you have any questions or concerns. So I will be talking to you soon. Take care. Bye-bye.